I think we can start. This is the second lecture for reinforcement learning. The goal for today is to cover chapter 2, which is on Markov reward process. So today we'll be adding the reward. So last week on Friday, we saw Markov processes. So today I'll be adding the reward to the model, not the action yet, so not the agent today, although I might have some time to start on chapter 3. So the topic of adding the agent will be really on chapter 3, and that should come on Friday. Although if I have some time, then I might start today. Questions before we start? Okay, so something I forgot to mention last week is the address for the GitHub where all the information is. So again, you have the scan of the lecture notes, you have the coursework, which is there, and then at some point I will also put there the solutions to the coursework. So I have to give this address because actually some student mentioned to me that you cannot find it, so it's not on Google yet because I just created that last week. Eventually it'll be seen, but it's a public directory, so you can access the material there. Don't push anything to the GitHub, just you can clone it, or you can just actually click on the material there to see it, and you can download some stuff from there. Okay, questions? No? Okay. Okay, so I'm going to start with this new chapter, chapter 2. Markov reward processes. Okay, so the acronym is MRP. Okay, so like last week, we have the state for the process. This will be denoted by S of t. The state is in some state space. What's important is that the time is discrete for us. So 0 is the initial time, and then we just run the clock in discrete time. And now what we're adding to this, to the model, is a reward random variable, which I'm going to denote by RT. So this is a real random variable, and it's given at every instant in time. Actually, maybe not time 0. So this is the cost or the reward giving for transition. So this is the cost or reward for a transition. We'll see this. This is a random variable correlated with a certain transition, st minus 1 and st. So it really depends either on the state before, the state after, or both. So it really depends on the transition. And sometimes it's a function of the two. So we'll see that in many of the cases, actually, the reward will be a deterministic function of the two states, or even one of the state. But to make this more general, we'll take this to be a random variable. And the way that the reward is given is via the transition probability for the whole system, including now the reward. And this is really the dynamics of the system. If I specify this transition probability, I have the dynamics. So now the dynamics will be specified by specifying the new state that I reach, and then the reward that I'm going to gain if I do a transition from S to S prime. So if I write this in full, then this is the probability that I reach some state S prime after some time. I get the reward at that time for making the transition to be equal to R, given that I start in the state S. Okay, so on Friday, we saw the transition probability purely as a dynamics involving the state of the system. And now what's added is the reward that is gained by making a transition. So if I put a diagram for this, then I have the Markov chain that I had last week. I start with initial state, I can make a transition, and then I can evolve the Markov chain like this over time. And the difference now is that I'm going to have a reward now sitting on top, which is the reward for making the transition. I could put the reward at the top of the arrow. It doesn't really make any difference. the way I'm going to write the model is that I have a reward that's coming from the transition, and I'm going to put this on top. Okay. There's no agent here, so I'm not moving or influencing the dynamics in any way to achieve the greatest reward. It's just there is a reward coming from the dynamics. So the reward is given as part of the dynamics. On Friday, I'll see how we can put an agent there, and then the goal of the agent will be to change the dynamics so as to optimize some reward. But for now, the reward is only part of the model as a random variable that's correlated to this and this at the same time. Okay, so these three random variables in general are correlated. Okay, so we're going to make a few assumptions on this, just like we did before. So we'll assume that this transition probability is homogeneous or autonomous, so it doesn't explicitly depend on time. So this is the same matrix for whatever transition you'll be doing in time. You can make this time dependent, you can make this time inhomogeneous, that's fine, but that's going to be more complicated.
The reward is correlated with ST minus 1 ST.
Yes.
So
I'm sorry. So here I should put something like this. Well, it's the same, right? So the reward, I'm gonna write the reward as being associated with this one, but really the reward is correlated with the two.
But here it looks like it reward at t plus 1 and the state at t plus 1 depends on only on ST.
No, you see, I have a joint probability here. So these guys are correlated. So given the state before, I mean, basically enacting a transition to a joint state, right? So this is correlated to this, so these two guys can be correlated. Okay, so there's no splitting assumption or simplifying assumption at this point. There could be, but so in many applications, actually, the reward depends only on the state before, or it depends only on the state after. And then we'll see this actually in the linear model that I introduced last week. But for now, I'm just putting the model in the most general way possible, provided, of course, I have a few simplifying assumptions. So again, I'm going to write this now. There's no action or agent at this point. Okay, this will come in the next chapter.
Right now, we're just kind of looking at some trajectory and just adding up what the reward, just
Yes.
like a score or something.
This is a score. I could add this. This is good. A cost, a reward, or a score that actually is accumulated along a given trajectory. But the point is that it can be a random variable. So I'm making transitions at random, and basically you imagine you have a random walker, and then for every transition made, the random walker received a kind of reward. And so our goal is to see what is the expectation of the reward that will come out of the dynamics.
Which is this difference between the equations and what you're saying. In what you're saying, it sounds like the reward is deterministic based on ST and ST, but that's not correct. The reward is probabilistic. So you could take the same transition and receive a different reward.
Yes, this is given by this probability, right? So for the same transition between S to S prime being fixed, this is still a random variable. And the way that this is assigned as random variable is totally described by this joint conditional, okay? Yep.
This is reward, the way that the reward is correlated with ST and ST minus 1, does it affect the evolution of the chain? It's not giving me like that. It doesn't so far. There's no effect.
No. So this is the point I'm going to go now, is that from this conditional probability, which really is the specification of the Markov reward process, right? If you're giving me the entries of this transition probability now, which is a kind of a tensor, right? Because it's got 3 entries. Before we had a transition matrix, now we have a kind of tensor transition. It's not important for us, but out of this, I can calculate now reduced conditional probability. For instance, I can calculate what's the reward distribution. The reward distribution is just the probability that I get a given reward, given that I was in a state S before. How do I do this? Well, I just have to marginalize the dynamics onto the state that I reach after, right? So we discussed this last week. I can always margin all joints, and this is something that will come in over again. This is the full model. Out of the full model, I can marginalize S prime, and I get this P of R giving S. So this will be the probability that I get a given reward, given that I started at S, regardless of what S prime is. So I trace out S prime. I can also obtain the transition matrix of the underlying chain itself. So transition probability, which will be the P of S prime given S. And this is obtained by marginalizing the reward. So if I trace out the reward from the dynamics, I get the pure dynamics of the underlying Markov chain. So this will be the dynamics of the underlying Markov chain. Okay, these are all useful, and then we're going to use them specifically to calculate what is the expected reward, which is, I'm going to denote this by rho S. This is the expectation of the reward given that I start at time t in the state S. So this basically states that I'm in a state S now at time t. I'm going to effect one transition. I'm going to get some reward for this. What is the expectation? What is the mean reward that I get from making a transition? This is what we also call the one-time reward, or the immediate reward. Yes.
Why are we calling both the marginalized just to reward thing and the dynamics the same?
It's a good question. I don't really have an answer except that I don't want to introduce a new name. This is a kind of transition probability for the whole dynamics, and this is a transition probability for the Markov chain dynamics itself. Okay. Okay, this is an expectation. How can I write it? You see, in order to calculate this, I only need this, right? So I'm going to write it explicitly by saying, this is the expectation over R, so I have to sum over R. I sum the value, and then the conditional probability. Everybody sees this? Fine. So this is a conditional expectation. This itself is giving my marginalization, so I can also write this as a double sum R S prime of R P S prime like this. So this is how you would actually calculate the expectation, but from reduced information that you get directly from the full model. So this is an exercise that we'll always do. Whenever I write an expectation, we'll try to write it in all the possible different ways that we can express that expectation. And ultimately, we want to write that expectation in terms of the model itself. So this is not the model specification. This is the model specification. So we have to be able to go all the way down to that level. Okay. Okay, let's have an example. I can have a look at the linear model that I had last week, this Mars rover example coming from the Stanford course. So I have 7 states. Not sure why I chose 7 states. I think the original model had 7 states, but really for my purpose, I only need a few. It just means that I'm writing more. And then I can go left and right. So I can put some transitions here. This will be part of the Markov process. Actually, I can put some probabilities. And I can also stay at those extremal states. I could also put actually arrows to stay in the intermediate states if I wanted. This will all be part of the specification. Okay. Now, where's the reward? The reward must be added to this. So we had 2 rewards for this. 2 rewards. We had R equals 1 if I exit 0, if I stay at 0. And I had, I believe, R equals 10, yes. R equals 10 for leaving 6 or staying at 6. Okay, so I can put this basically, I could put actually the reward here. This will be better. So I get a reward for this transition or this transition. And here I have a reward 1 for this transition, staying at 0, or this one. Okay, so you see the reward is really added on the Markov diagram. Okay, now you see the reward as a special structure in this example because the reward only depends on the starting state. It doesn't depend really on the state I'm going to reach in this case because the model is linear anyway. So here the reward is really a deterministic function of S, not S prime. So I can calculate then the expected reward easily. So I want to calculate this. So I need to calculate the expectation for every starting state. So what will be the expected reward if I'm at the state 0? I get 1 whatever I do, right? So this is going to be 1 here. You see this? I'm not assigning different rewards for the two transitions. So regardless of the probabilities that these two transitions will have, I'm going to get 1 anyway. So the expected reward in this case is trivially 1. Okay? If I sit at 0 and I do any movement, the expected reward I get is 1. What will be the expected reward if I'm in the state 1? 0. I don't get anything for those states, right? So I'm going to get 0, and I am going to get also 0 for 2, all the way to 6. And 6 now will be 10, because whatever I do from 10, I'm going to accrue a reward 10. Okay? This is a very simple model. I'm not assigning different rewards for the different transitions from 0. I could, but we're not going to do this. Same thing here. So this is a really simple reward, but we'll see that we can make this more complicated actually in the control task when we get there. Okay, so I have that list. You see it's a vector, right? So I can also plot the reward. So I can say, this is my state 0, this is my state 1, 2, 3, 4, 5, and 6, and I can plot the reward. So I have a reward 1 for 0, then I have 0, 0, 0, 0, 0, and then here I have 10. Okay, and so this will be my row of S as a function of S. I'm plotting this explicitly because this is the kind of plot actually that we will need when we get to the Markov decision processes. And in the coursework already, you have to produce a plot like this for the Markov reward process for this particular example. So this is question 2 in the coursework. Okay, so after this lecture, you'll be able to start on question 1 and start also on question 2. In fact, you'll be able to do question 1 entirely, and then you can start on question 2, and then with the material that will come later on, then we'll be able to gradually advance in the coursework. Okay? Okay. This is only the immediate reward that you get from making a transition, but I've mentioned this last week. In order to do reinforcement learning, the agent cannot base itself on only immediate reward. If you want to achieve a task like walk in a maze, you have to see in the future or imagine the future and then base your action on future reward. Okay, so this is a very important concept, and this is the concept of return. So what is the return? Suppose I fix myself at some time t. I'm going to call the return from t to be the sum of all the rewards that I can get from that time. So I'm in some state st. From that time for the first transition, I'm going to get a reward r plus 1, t plus 1. Then after this, I'm going to get another reward at t plus 2, and then so on all the way to the future. Okay, so we're going to call this the present. With my yellow chalk. This is the present, and this is in the future. So the return is really a quantity that looks into the future. It's the sum of all the rewards. So I can put a diagram actually to show this. So again, I'm starting at s equals 0. I have S1, S2, S3, and then so on. And then here I actually got a reward 1, reward 2, reward 3. And then I could say, okay, what's the G2? G2 actually will take into account, if I put some colors, all of this. So this will be my G2. It's looking into the future for all the rewards. So I'm going to have S4, I4, and then so on. So the G0 actually will be the sum of all the rewards. The G1 will be the sum of all the rewards, but starting from time 2 and then so on. Okay, you see, so it's the sum of all the rewards in the future.
Don't we need a horizon to make this convergent? I mean,
yes, so I'm not talking about the horizon for now, whether this is convergent. We'll do this in a minute, actually, with either cutting the temporal series or by putting some coefficient that will make this convergent even on an infinite horizon. For now, I'm just putting this for the idea that for the control and then ultimately for reinforcement learning, we need to consider the rewards in the future. So this is the return. It's also called the cost to go. And I like that name because it really says actually what it is. It's the cost that's going to come. So it's the cost to go into the future or the total reward. So the question brings me now to where do I stop counting in the future? So there are two types of learning, or in this case, just dynamics, because there's no learning as such, but I can stop now counting the rewards to a finite horizon, so a finite time. So this will be a finite process, or I can keep on adding, but then I need to make sure that the return actually will converge to a certain value. So there are two types of process that we'll consider for Markov reward processes, and then we'll consider them also for the Markov decision process. So the first one is what we call episodic process. In this case, we'll stub this to some value. So GT will be RT plus 1 plus RT plus 2. And then we'll stop at some capital T, and that's the end time. T is the end time or the final time or the episode time. So here the process actually terminates. Process terminates. So this will be relevant actually if you imagine a task and then you have to do the task in a certain number of steps. Okay, so then what you'll be summing in the future is only depending on how many steps remain to achieve the task. Okay, so this is something we can consider. So if I look at backward in time, you see, I'm going to have my S0, S1, S2, and then I'm going to finish at ST. Okay, I have all the rewards. I'm going to be drawing lots of these diagrams, you see. And now the question is, what's the reward? So if I start at the end time, what is the GT? What's the GT for the final time? It's going to be 0, okay, because there's no cost to go at that point. If I go just one time steps before, so T minus 1, then what will be the cost to go? It's going to be the last one that I get, okay? So the cost to go is always going backward like this. So if I write what will be the cost to go from the initial time, then it's the full cost. Okay, so it's really the cost to go, and then this will be necessarily finite because you have a finite horizon. Yes? No, no. Yes. It's all encapsulated again in the transition for the dynamics. It's something we can consider. And yes, so you see here, we're dealing with the expectation of the one-time reward, but ultimately we'll be dealing with the expectation of this. Whether these are independent or not, actually, because the return is a sum, we'll be able to deal with this and no problem, okay? Okay, if I look at this, for instance, if I run this kind of example, this is not terminating, right? Because it's just walking around, and even if I get to the endpoint, I'm just looping on the endpoint or decide to come back and then so on. So this is not terminating, but I could terminate it. So as an example, just a very general example, I could have some start state, and then I could transition to some on state, and then I could terminate this into sub-state, a stop state. So I start somewhere, something is going on here, maybe there's a dynamics actually that returns here, and then I have some rewards. I'm gonna have a reward here for starting, and then I go somewhere else. When I reach that state, I stop here. So there's no loop actually coming back. I just stop there and then the process will terminate. This is one way actually of making a process terminating. You just have a state that you call the stop state. Now you can make this process go on and on if you had a loop in the stop state just to continue, and then you can add loop. And so if you don't want your process to stop, then this will be called a continuing process. So a continuing process will be a process for which the horizon is formally infinity. So the process goes on and on. Process goes on and on. And again, you can do this by putting loops into a stop state. So the message I want to put here, I'm not going to put in writing, but I can say it. If you have an episodic process, you can make it continuing by putting a self loop and putting more loops to have more dynamics. And this is an example. So I could say here in the dynamics, when you reach 6, you stop, and this will be a terminating process. Or I can say, no, I've got more loops there, and then you just continue the process. Of course, in simulation, we'll always be terminating the process somewhere, but for the purpose of defining a model, you don't need to actually make it terminating. Yes?
Why is such a loop if I'm staying in the
if I'm staying in the same state 6, then still it is counted as continuing process, but the state itself is not changing. Say for example.
Yeah, but it's still a continuing process, right? Same here. Actually, even in this dynamics, I can decide to, there's a possibility that I stay in the state 2, state 2, state 2, state 2, state 2, and then up state 3. The fact that you remain in a state is not a problem on its own, right? So you're just not moving, that's okay. See, if I put the reward somewhere here for staying in state 3, ultimately the learning agent will want to stay in state 3, right? So that's a possibility, a transition that will be reinforced. Here, there's no reinforcement, right? But if you imagine reinforcement learning, so the fact that you're staying in a state is not a problem on its own. It's not terminating. Right, but now there's a problem.
Excuse me, one more thing.
Yeah.
What criteria should decide on, like, where should one terminate a process, kind of?
It depends on the application. It's totally up to you or the application itself that you consider. If you play chess, chess is a terminating game, right? As soon as you reach a certain goal, it's finished, but it's a random time for terminating. It's not a fixed time for terminating. There's some other games or some other tasks that you can imagine just doing over and over again. And so these are continuing tasks. Now, it just so happens that theoretically, it's easier to consider continuing tasks and not terminating tasks. So for the purpose of doing the theory of reinforcement learning and dynamic programming and all the theory that comes with it, I will always consider continuing tasks. Okay, but this is just a simplification for the purpose of teaching. But basically, everything I'm going to say can be adapted to episodic tasks, but you just have to tweak them a bit. It's easier to consider this because I assume that the dynamics is stationary or time independent, and I'm going to look at an infinite horizon. So I can do everything in a stationary way. And that simplifies the analysis. But what I'm going to discuss, the fact that I actually focus on continuing processes doesn't mean that the theory is different for episodic processes. The theory is more or less the same. You just have to account for the fact that you have to finish something. But now there's a problem with the continuing task because if you sum the rewards over an infinite time horizon, it's going to diverge. Okay. So to cure this, we're going to introduce something that we call the discounted return. And then we'll do this for two reasons. So the discounted return will be, it's the same symbol, so I'm not going to change the symbol for it, but it's going to be the reward that you get into the future, but you introduce a gamma factor for just weighting the rewards that come in the far future. Okay, so what do we, sorry. The gamma is what we call the discount rate. It's a number between 0 and 1, and 0 inclusive, 1 inclusive. And you see it's a geometric sum, so if you take the gamma actually strictly smaller than 1, then for a continuing task, the return will be finite if you choose from 0, but strictly 1, so you don't take 1. Okay, because it's a geometric series, so it's going to converge. It depends on how R is defined. It's true. Okay, but R should have some nice properties, so that there's no assignment to infinity, so R cannot take the value infinity. It's a random variable, so I would have actually to discuss what I mean by convergence, because now do I mean convergence in probability or convergence for sure, or so I'm not going to do this. I don't want to get into the technical details. You kind of see that, you know, for a given sequence of reward with probability 1, this is going to be finite, provided I have some assumptions, some nice properties for the reward. The reward is not too crazy. In particular, if the reward is discrete or has a finite value or finite support, this is finite for sure. Okay, so the discount is introduced for two reasons. One is technical, is to make the return for the continuing process actually finite. But there's something actually more fundamental, which is that as an agent, and again, let's advance in the learning phase that we have in Reach, but if I want to do a task looking at the reward in the future, not all the rewards should be weighted equally. Okay, so I might want to influence my actions depending on the future, but in most cases, the very far future is not as important compared to the immediate future. And this will be actually taken care of by putting a gamma factor here. You see, so if gamma is strictly smaller than 1, this is some number between 0 and 1, but this will be smaller. So I'm weighting down actually the future rewards in the future. And so this is a good thing. Okay, so you have two reasons for considering this. And really, as a controller, this is the quantity I want to maximize. I need to fix a certain gamma, and the gamma that you choose actually would depend on the application. It really depends on how much of the future you want to see and how much of your action you want to depend on the future. Yes.
This is a, yeah.
Sorry, he's got a microphone. It's going to be easier to.
So this is some classic economic model, right? Because in economics, you always have a discount rate for the future. But for many other tasks, like the chess task that you just mentioned, this is not what you want to do. You just want to maximize the reward at some given point of time in the future.
Yeah.
You don't care about immediate losses.
Yes, but I think I would claim that chess is more of this type where it's terminating. So you can deal with the reward actually in a way that doesn't introduce discount. But in the Go game, for instance, there is a discount. Okay, because it's true that you have an overall goal to reach, but you still want to prioritize some actions depending on the rewards that you get in the near future, not in the far future. Hoping, of course, that the actions that you're determining or choosing in the near future will influence your future goal in the far future.
Say, I want to look at the reward up to a time t. So the way you defined it was you summed up to a terminating time, but you could instead choose the first n terms or something like that. And then that would maybe fit both chess and Go.
Yes, you can do this, and this is being done. So you can define a finite horizon reward, and then you can move that window. For the purpose of teaching, this is not so good because it introduces lots of new notations that I would have to take into account. So this is the situation we're going to take as a practical situation. It's quite practical even for applications, and it's easy to treat on the blackboard. Okay, but yeah, around this, you can imagine many variations for sure.
Just a related thing, and maybe, yeah, feel free to shoot it down if it's not relevant, but this would create sort of a greedy agent, right?
Yes.
And so,
Depending on the value of gamma. Of
Right.
course, there are two
and
extremes.
if you don't want a greedy agent, you'd want gamma to be larger than.
Exactly. So this is what I want to add here. You have, for instance, the myopic case where you don't see the future is when gamma is equal to 0. Okay, so in this case, you really look just at the immediate reward. So in this case, the return is the immediate reward. So here you're just maximizing. We're talking about agent, right? There's no agent in Markov reward process, but I'm really anticipating as to why I introduced this model. In this case, the action will depend only on what you get immediately. This is an extreme. The other extreme is the far-sighted. So you want to weight stuff really far into the future. So you take something that's not quite 1, but it's close to 1.
Is there a fundamental reason why you have taken exponential decay and not something like polynomial decay?
It's going to make things very easy for the theory, but you can vary this also.
I see.
Okay? So let's write this in different ways.
Just one question, like how will you choose gamma? Like what's the freedom? Like you can choose any kind of.
You can the gamma is a parameter of the process at that point.
Okay.
It's a parameter of the model.
So it depends like what model, what physical model you want.
We'll actually test this with the examples, with the rover model. We'll see the influence of gamma. Then you can test this also for all the examples that we'll be discussing in the coursework. So there are various control tasks in the coursework, and then you can change the value of gamma to see how the solution changes. And it's quite interesting because it realizes this idea that you're basing your action based on the future. So you can weight the future in different ways, and of course, it's going to lead to different optimal controllers. Okay. And this is an intuitive idea too, right? I can live my life optimizing my afternoon. It's not a good way of living. Okay, but at the same time, I cannot live my life to, 30 years in the future. I'll be freezing myself too much at the present, right? So you have this tension also in reinforcement learning, and the way that the learning is achieved, or even the speed or the convergence of the algorithms towards good learning policies actually will depend on gamma quite a lot. In the courseworks, I'm going to give it to you. I say, do the simulations for this gamma because I'm going to give the solutions for a given value of gamma. But this is really a parameter of the model, right? So I should put a little gamma here. The returns that you'll consider will depend on gamma. This is implicit at this point. Now, let me write that return. There are different ways of writing the return. Right now, I can write the return for a continuing task as I'm going to start from 0 and then run to infinity with that geometric sum. P plus 1 plus k. Okay? Now, I write this, but we should check the indices, right? So at k equals 0, I have gamma to the power 0, that's 1, and then k equals 0, so I'm summing the first return at RT plus 1. That's good. Then the second time step will be k plus 1, so this one is weighted by gamma, and it's going to be t plus 1, so t plus 2. So this is good. At the same time, I can write this as RT plus 1 plus gamma t plus 1. Okay, and this will be very important. So this form is really important, and in a sense, it explains what I'm using this geometric kind of discounting because it introduces a nice structure between the return at time t and the future return at time t plus 1. Okay. It's a convenient choice. Again, you can do variants around this, but it just makes the theory more complicated. So we'll try to understand the theory of reinforcement learning for an easy case where I'm considering a continuing process, so no finite horizon, and a geometric discounting. And this will lead to a kind of easy theory. It's not so easy, but it's easier because of this structure, the GT and the GT plus 1. Okay? And then look at the indices, right? Two. Two. So if I look at my diagram, which I had here, I mean, this is bad teaching practice now because I'm drawing over something that came before, but I have the G3 here. Here I had a certain gamma. So you see that there's a gamma actually that comes with it. Okay, so far so good. So I have the dynamics, I have the reward on top, and now I consider the return, not the immediate reward, in order to be general and then pave the way to reinforcement learning. Now, what I really want to calculate, we had the expected reward now that we looked at, but now I want to look at the expected return. And the expected return will be called the value function. And then we'll explain why we have this name of value function. So what's the value function? The value function, I'm going to call it V of S. It's the expectation of the return at time t, given that I start in S at time t. Okay. So this is essentially the value of the state S. If I start in a certain state S and I have this full dynamics in front of me from that state, it's going to incur many different rewards along the way over the infinite trajectory starting from S. And then it's going to incur many different returns at random. And so I can take the expectation of everything that comes into the future. And this is the value of the state S. I'm not putting any time t here. Why does it not depend on t? That's because I'm assuming that the dynamics itself is time independent, and I'm looking at the far future, at the infinite future, right? So it doesn't matter if I look at my return from the time zero. If I move by one time step and I look at the infinite future, it's going to be the same value again. Okay, so this is a time independent quantity because of our assumption of using time independent dynamics and because of our assumption that we're looking at continuing tasks. This will depend on time if you looked at finite horizon. If you looked at terminating task, this would actually depend on the final time and the time at which you calculate. Okay, and so the theory is more complicated. Okay, so let's draw this just to explain and diagram what I said. So you start here at time t, you just fix that state, you just say, oh, this is equal to small s. From this particular state, you're going to transition to a bunch of states. So you can repeat one time a simulation, you'll get to a new state, you can repeat the simulation, you'll get another state because this is random, and then you're going to get a reward. And then you just run this dynamics forward in time in an infinite way. So here you have RT plus 2 and so on. So here there's no discounting. Here there's a discounting. Let's put another one just so that we understand. So here I'm going to have gamma squared RT plus 3. So my horizon for the discount is here. This is my GT. The GT will look into the future like this, and the discount comes on the second time step. But now you see, if I look now, if I take another color, if I take this new horizon, GT plus 1, then you see I just have to take the gamma out. So my GT is this reward plus gamma GT plus 1. Okay. Okay, so I'm going to put some text. This is the value of S of the state S. Doesn't depend on time. And moreover, if I take gamma equals 0, my V of S is just the expectation we calculated before. It's the immediate expectation of the reward. Okay, so this is the expected return. This is the expected reward. But if I'm myopic, then the return is the reward. I forgot to mention this, but our rho of S also doesn't depend on time, right? For the same reason. The one-time expectation does not depend on time because the dynamics is assumed to be time homogeneous. Okay, so let's look at the linear example again. And then I'll basically finish with this. There'll be a bit of theory afterwards, and then I think that will be, oh no, we started at 3:30. No, we have way more time. I was looking at the clock as if we're. Is it? One minus gamma. No, I think it depends on the reward structure. I'm not so sure actually. No, we'll see an example just here actually. Let's go back to this linear model. But now, and then we can discuss that question for this one. But I'm going to take the linear model in a very particular way. So I'm going to I have the states. And I'm going to choose a very trivial dynamics where I only actually move right. And when I reach 6, I stay in 6. So this is a continuing process. It will not stop. Okay, and then I want to sort of guess. So don't forget, I have the R1 here, and I have here the R10. Now, the only way I'm going to get 10 is when I reach 6. As soon as I stay in 6, I'm going to start adding these 10s. But I have a R equals 1 when I go out. Okay? This is fully deterministic. I'm going out for sure. So I have these rates, these transition probabilities, they're all 1. So there's no way of staying. So this is really a trivial Markov chain. Okay, this is actually part of the exercise, part of the coursework. Okay, so first I'm going to plot again what we had as our rho. Okay, so the rho will be in white. I had the value 1, and then I had the value 10. It's not plotted to scale them, but I just have the value 1 and the value 10, right? And I had zeros like this. So if I put lines, then I have something like this. This is my rho of S. This is the one-time reward, expected reward from leaving the state. If I leave 0, I just get a 1. If I have 6, I have the 10 like this. Okay? Now I want to imagine what will be the V of S. But now, what's the V of S for something that's strictly greater than 0? So if I start in the state 1, will V of S be greater or equal to rho of S? It's going to be greater because I'm going to see in the future. The gamma makes me see in the future. So the value of that state already sees the fact that ultimately I'll be reaching 6 and then adding all these reward 10s in the future. Okay? So here I'm going to have my V of S. I don't know what the value is actually. It's something that will come from the coursework. But there'll be for sure a value greater than rho. Because I see in the future, so I have more rewards coming, and then the weighting of those future rewards will depend on the gamma. So if gamma is really close to 0, I'm expecting the VS to be close to the value here. But as soon as I switch on the gamma, I'm going to go above. Okay? Same thing here. Here I have a value 0 of immediate reward when I go out of this state. But now because I see the future, there's going to be a value here. In the state 2, there's going to be a slightly higher value because now I'm closer to the goal of reaching the state 6, and so of reaping rewards 10 at each time I'll be staying in 6. And same thing here, and here there'll be a better reward. Okay, so this should be something like this. And this should actually increase up as I increase gamma.
if it starts from 0 in the first step, it's definitely going to 1, right?
Yes,
But then the rewards after that, there's no reward.
there's no reward, but eventually I'm going to reach the state 6. In fact, in how many steps? 1, 2, 3, 4, 5, 6. On the 7th step, I'm going to have a reward 10.
Oh, okay,
So the return includes that reward, but it's been weighted down by gamma to the 7.
Okay. So it's just going to 1 plus gamma.
Yeah. Okay. So again, it's seeing in the future. So the fact that it's been lifted is already anticipating on the fact that I'm going to reach the state 6, and then the rewards will be added at that point. But it's not increasing by a lot because, of course, I have the reward here, but it's only increasing. In fact, the gap here is going to be smaller than the gap because this guy sees the future, is closer to the future. It's going to reach that state in 5 steps. And so the gamma will kick in at the 6th step. Okay, and then so on like this. And so you see that the value of the state is not something, it's above the immediate reward because you're reaping rewards. Of course, here the rewards are positive, so it's lifted up, right? If I put negative rewards into the picture, this gets complicated. But I just want to show that the return takes into account the future, and the future is weighted by gamma, and all of this is contained in the V of S. Okay, so in a sense, if I give you a Markov reward process as a bunch of different transitions and given rewards, what you want to calculate really, the full prediction of the behavior of the Markov reward process is all encapsulated in this V of S. It tells you how the return behaves if you start in specific state. Again, for a continuing process over an infinite time horizon. Okay? Questions? This will be crucial for the reinforcement learning. So when we get to Markov decision process, we're going to see those diagrams again and again.
Yeah, so the way this has been defined, it looks like you're not paying a price for increasing gamma, right? I mean, the more gamma you have, the more is the discounted return. I mean, shouldn't we divide by something so that...
Oh, yes. Now, of course, this will depend on the application and the meaning of gamma and the meaning of this reward. If you have a kind of economic model where the reward is actually a price to pay or something, and then the gamma will be a parameter of the system, and you want to change that gamma, there will be a meaning to increasing gamma or decreasing gamma. Here for the theory for now, I'm not actually mentioning any of this. And in fact, I just said that for us, gamma is a parameter. We'll see that for us, gamma will be a parameter for the learning task on its own. Okay. But in many applications, gamma has a significance. It could be an interest rate, right? It looks like an interest rate. No.
Yeah.
Oh, so what is the real value of GT? Is that the question, whether the values of GT have absolute meaning or just the relative value of GT? Oh, okay.
Exactly.
This is a different question. So here actually the V of S has an absolute value, right? It's the actual expectations of the returns starting from a certain state S. Of course, it's going to depend on gamma. So I could put the gamma index just to show explicitly that it depends on gamma. I'm not going to do this. Again, I said that the return depends on your choice of gamma. Okay? And this really has an absolute meaning insofar as the rewards themselves actually have absolute meaning. If I give a reward 10, and if I give a reward 1, I get an actual value function which is determined there. Of course, I can change these rewards without changing the ratio, and I'm going to get something very similar. Okay. So often what's interesting, especially when we get to Markov decision process, is not the absolute value of the rewards themselves, but the relative values. Okay, that's what's important for achieving a control task. And it's related to something I mentioned last week, which is that when you define the reward for a task, often you can define different types of reward, and then you can achieve the same task. Okay, so for the maze example, for instance, I said, I'm going to give a reward -1 for all the steps that I take, as opposed to giving a reward of 20 for reaching the goal. If I train an agent on this, I'm going to get the same solution at the end. So there's something called reward design. How do you actually define the reward to achieve a certain task? But this is not part of this chapter now, right? Because for this chapter, I'm defining the Markov process and the rewards on top, and so this is given. We're not playing with this at this moment. Okay. Now, the reason why I'm going over this chapter is for teaching. I could have started with Markov decision process directly, but in my experience, it just makes the learning more difficult. So it's easier to start with Markov process first. We understand that part. Then we put the reward. Then we understand that part. And then on Friday or maybe today, we'll add the agent, and now we can fully understand. And one equation, especially that's going to come in the Markov decision context, is what we call the Bellman equation. And the Bellman equation is not so clear actually when you introduce it in the context of Markov decision process, but it's very easy to understand in the context of Markov reward process. And that's the following equation. So this is an equation for the value function, and it has this form. So by definition, this is just the expectation of the return, given that I start with that. Now, I can use the iteration equation that I have here to say that this is the immediate return plus gamma, the full return. But you see, in expectation, inside the expectation, I can also write this. This is the expectation of the value function when I start at that state. So I end up with a kind of bootstrap equation where the value function actually appears inside. Okay? Let's make sure everybody understands. This is the value function, that's the definition, that's the expected return. Here I'm just using the telescopic form of the expected return, that comes from the geometric form of the return. That's good. And here you see this is the return, but not starting from st at times s plus 1. This is the return in the next time step, so it corresponds to the value function when I start in that particular state. Okay. So this is the Bellman equation, and then let's try to make it more explicit. To make this more explicit, I need to write all the expectations explicitly. So explicit. So the value function first is, I don't have actually a distribution for G, so I'm just going to write the expectation here. So if I start with equation 1 here, this will be equation 1. This is I sum over the reward, okay? I'm going to take this is my conditional expectation if I start in the state S. This is the immediate reward I'm going to take, plus gamma. And now I have to sum over all the S prime that I'm reaching. And this will be the value at the S prime that I'm reaching, like this. Okay, we all see this? Okay, maybe before I go there, any questions over this? We're all good with this? Okay. Yeah, maybe I went just a bit too quick. So let's do a diagram. Whenever in doubt, let's put a diagram. So I have my state st. I fix this to the value s, right? This is going to trigger a transition to st plus 1. This is a random transition, right? So st plus 1 is a random variable. This is actually fixed deterministically on the conditioning. Okay? Now, my gt starts from here. Okay? So at this point, the v of s is actually, if I use another color, my v of s is calculating like this from this return, right? But suppose now if I look at all the states that I reach here, I could actually go to another state. And here I'm going to have now the gt plus 1. Okay, I'm not consistent with my colors. This will be now the gt plus 1, right? So from the point of view of this guy, all that comes after is also the return, right? So I have a value function actually for starting here. T plus 1. Okay? It's just that the V inside, the state that I take inside, is a random variable. Okay? So the value function at times S, at the state S at time T, is the reward that I get here. So that's the reward that's sitting on top of this guy. Plus the discounted return. So this you understand, fine. But the return itself that comes in the future actually is the value associated with the state that you can reach in the first time state. Right? But you have to treat it as a random variable. So this is why it is a random variable inside. So when you take the expectation, implicitly, you have to take an expectation over all the states that you reach at time t plus 1. Okay? And so this is what we're doing here. So V of S is the expected one-time reward. So I need the P of R given S to calculate this. And then it's an average of the value function in the future state that you reach. And I need the P of S prime given S to do the average over this. Now, at this point, we have a look and then we see this is not part of the original model. This is not part of the original model. I should be able to express those expectations only in terms of the model specification. So I have to go one level above where I have R S prime R given S. Now this is the model. So I've put back the S prime, which I marginalize in order to get here. And the same thing here. I need to put the gamma, and now I need to put the R back in order to have S prime R given S. So that's the full expectation that you would actually have, you would need to calculate in order to get the value function. But now you see it's an equation that involves S on the two sides. Okay, so we need to solve for this value V of S. So in a sense, we want to isolate the V of S in order to express what the V of S is in terms of the model. Because the goal ultimately, again, is to calculate what the value function is. Okay, so I'm going to do this with linear algebra. The first thing is this guy really is nothing but rho of S, right? This is the expectation of the one-time reward when I start in S. This now is gamma, and this I'm going to write as, this is an expectation, it's an expectation of the full model as a matrix, P, this one here, which is multiplied by the V. So we saw this on last Friday. The evolution of the probability was a row vector multiplying a transition matrix, whereas expectation was a column vector that is being multiplied by the transition matrix. Okay, so here we take this. You see, this is the transition matrix multiplying this vector V. So this is my capital P, that's the transition matrix. So the equation I have is really a linear equation for S, for V of S. So in matrix notation, I'm going to have this equation. V is equal to rho plus gamma PV. So let's write this now in column. Here I have V of S. That's the column vector containing the value function for every state. That's my rho of S. That's my immediate expected return from starting from any of the state S. That's a column vector. Gamma is just a number. P is actually the transition matrix like this, but in transition matrix term, it's S to S prime. That's the square matrix, and that's my V again, but now like this. Okay, so you see that as you multiply the transition matrix onto this, it's going to create this expectation. So this is a column vector square matrix multiplication. And as soon as you realize this, Now you have a linear equation with vectors v on the two sides. Okay. Okay, so that's the vector form of the Bellman equation. So that's the Bellman equation. It's a recurrence iteration equation for the value function. This is the Bellman equation written in explicit form in terms of a bunch of expectations. And this is the Bellman equation written in vector form. Okay, and the solution, of course, is this. V will be equal to the identity matrix minus gamma p. You take the inverse of this and you multiply by the vector rho. Ah. So now you're thinking about this one, right? But what I consider to be my p is actually not this. This is not a transition matrix. I said it's kind of a tensor. What I consider the p is actually, let's put it in color here, it's this p here. So it's really the Markov p dynamic. After marginalization of the reward. Okay, so this is a good point. Oh, it should be yes, yes. So this is the result in the position S. This will be the result. Thank you. Okay, so let me put it here actually. So this is the transition matrix. But trace out the reward. So it's only the Markov dynamics. Okay. This is useful now because we have an explicit expression of the value function. The P actually will come from the specification of the Markov reward process. So in order to get to this P, you need to trace out R. That's fine. You get a matrix. Gamma is something you choose. Identity is given to you. Take this matrix, calculate the inverse. So the complexity of the solution is just the complexity of calculating the inverse. And then this matrix, you multiply by this column vector. It's going to give you a column vector corresponding to the value function of all this. This is nice. And this is because the Bellman equation is linear. We'll see actually that when we get to Markov decision process, the Bellman equation, we're going to have a Bellman equation, and it's going to be nonlinear. And so that the whole problem of reinforcement learning is that you have to deal with nonlinear equations. Okay, but we'll see how we can do this. So here it's fairly nice. Okay, so I'm going to finish just by explaining how we're going to apply this in the coursework. The framework really is the framework of this linear model. Okay, so question 2 in the coursework is about this linear model explicitly with this dynamics. And the question is asking you to calculate the value function for this Markov reward process.
So I have a question.
Yes.
I mean, under what circumstances is this matrix invertible?
So this is always invertible if for the gamma actually different than 1 and 0, no, different than 1. So this is a good point. There's always a solution for gamma strictly smaller than 1. Okay, that's because it will make the reward finite over an infinite horizon. This is not so clear actually in the way that we write the solution as this linear algebra solution, but it's guaranteed. It's just because the reward is finite. So there's a finite value function for each state.
Okay, thank you.
The dominant eigenvalue of P is 1. Is 1. We saw this on Friday. The dominant eigenvalue of P is 1. So that makes that is the source of the problem.
But as long as gamma is less than 1, it's still.
Then you're okay, exactly.
Yeah, okay. Yeah.
So gamma is this regularization parameter in a sense, but it's there to regularize. You can see it as regularizing this linear algebra solution. You can see it as a way to make the infinite return finite, or you can see it practically in engineering term as something that's just weighting the future. But this is a good point. Okay, so yeah, it's always one. It has nothing to do with the particular Markov chain that you consider. Whatever Markov chain that you have, the transition matrix has a dominant eigenvalue equal to 1. That's the steady state, if it has a steady state. Okay, but even without steady state, it has an eigenvalue 1 because of normalization. Okay, yes. Okay, so we need to practice this. It's nice for me to discuss all that theory and then writing the theory, and then I like theory, but there's really no understanding without practice. And so this is why we have the coursework, and the coursework has a number of sections, and then we're going to go gradually over that coursework. So there's no way we can actually finish the coursework today. We can only start on the first 2 questions, question 1 and question 2. And this particular solution is the subject of question 2. So question 2 is about this linear model specifically. And so you will calculate in Python, you will draw this plot for the one-time expectation, and then it's asking you to plot for different values of gamma what the value function should be for these values of gamma. So what you need to do is to encode in Python these transition matrices, fairly easy, and then solve this equation in linear algebra, numerical linear algebra. It's fairly easy using Python, using the inverse function in NumPy, in order to find what the value function is. And then you can plot it for different values of gamma. And then what you'll see is exactly what we intuited about the fact that the value function should go up as gamma is increased to 1. When gamma is equal to 1, there's no inverse solution, and so it's infinite. Okay? So get to practice this. And then Umesh is our teaching assistant, so if you have any questions, you can email him, or if you see me around, then you can ask me questions too. But it's really important that we get to practice this, even for the faculty here. So on the GitHub, yeah. We can also have a few copies printed with the academic office. So this is question 2. Question 1 is, and I'm going to describe the question 1 now, is what we call the bandit problem. So I'll finish the theory for today. So we're done with chapter 2. So I'll start chapter 3 on Friday. And I just want to describe before finishing is question 1, which is the bandit problem. So the bandit problem is like a Markov reward process, but even simpler, because there's no dynamics. You only choose a random variable, it's given a reward. Okay, so here it's a Markov reward process with no evolution. And this question is interesting because you can play with the notion of reward and try to learn what the reward is without actually caring about an evolution. So what you have is that you have a certain state and it gives you a certain reward. I'll explain the name actually bandit problem in a minute. So the state for us will be a state A and the reward will be R. And then you get a reward at random with a certain probability P of R given A. So it's a bit like a Markov reward process, but I'm not actually defining any dynamics for the state. I'm just taking an action, it gives me a reward. So what I'm going to do is that I'm going to take an action 1, it's going to give me a reward 1. I'm going to take a second action 2, it's going to give me a reward 2. And then I can repeat this many times and I get many rewards. All of these rewards are random. Okay, and what I can calculate is the value of a certain action, and this will be the expectation of the reward given that I take the action A. So this bandit problem actually introduces now this notion of action. I push the dynamics away. I don't want to care about this for now, but I want to discuss the action. The action, the choice of an action gives me some reward. So I want to discuss this. For the Markov reward process that we'll be practicing in question 2, you only have the dynamics. You're not making any action. There's no agent. And so there you want to calculate the value function. So here you see I have a different value function. It's a value function that's related now to taking an action. And then what we'll do on Friday is to merge the two. Okay, so for this question, it's going to be easy. I'm going to have 3 actions. 0, 1, 2. So I number everything as in Python from 0. And the reward actually will be a normal random variable. If I choose the action 0, it's going to return something at random Gaussian distributed with the mean 0. If I choose the action 1, it's going to give me a different Gaussian. Okay, and so it's clear what the expectation should be according to each of the action. The Q of A for A equals 0 is going to be 0. The Q of 1 will be 1. The Q of 2 will be 2. But the point of the bandit is that you don't know first what the reward is. Okay, and the name bandit actually comes from slot machine, essentially. So the problem that you have to imagine is that you have 3 levers. And then you can choose to actually pull a lever, and it's giving you some money at random according to these distributions. But you don't know this, right? So you're a blind user to begin with. And the goal, of course, is that you want to find the arm that's going to give you the greatest price, right? But this is a random price that's attached to this, right? So it's clear that the winning lever is here, right? So the slot machine with these levers is called the multi-arm bandit, because the bandit is actually stealing money. The casino is stealing money, okay? So in the way that I phrase it, you gain money, but really with the casino, you never gain money. But anyway, so that's the bandit. So this is a 3-arm bandit problem, because I have 3 selections, 3 actions. Okay, so the distribution for this will be, for the first arm, you have something like this. For the second arm, you have something like this. And then for the third arm, you get something like this. So again, the third arm is the winning arm, but as you start playing with this, you don't know. So maybe you start with the 0, and maybe you get a very big reward. Okay? Then you go with the 1, and then you get a small reward. You get with the 2, and then you get a smaller reward. So you might think, oh, the 0 is the winning one, right? And so then you have to redo this in order to learn asymptotically and probabilistically what's the winning lever. Okay, so you see where this is going. In order for me to determine what's the winning lever, I need to do some exploration. I cannot exploit to begin with, right? Because if I only exploit on the biggest reward that I had, and I'm start now pulling the lever 0 and say, this is the winning lever because it gave me the first largest return, that's not good, okay? So first you need to explore to see what the possibilities of the rewards that you get. And once you have a good idea of what the distribution of each of the lever, then you can start exploiting to get your maximum reward. Eventually you'll see that the biggest mean is actually obtained by pulling number 2, and then you just continue pulling number 2. But before you get there, you're gonna need some time. Okay, so this is a very nice problem to illustrate this notion of exploitation and exploration. The second question really is about this value function and then understanding what the value function is. On Friday, we're going to put the 2 together, because now we're going to have an action that can select different dynamics, and so the action will have a value also. Okay, in the same way that here, each of the 3 actions have their own value. Yes? Yes. Yeah. So here the states are actions. So this is number 1. This is not part of the Markov reward process, but it's a kind of kindergarten exercise in order to get us to Friday about Markov decision process. Because a Markov decision process will be a Markov reward process on which we put now an action variable. So I want you to practice this notion of action. And the easiest way to do this is to get rid of the evolution. Just consider the action. And that's a bandit problem. It's called a non-contextual bandit. There are many variations of the bandit problem, right? You can have correlations between the actions. You can have correlations between the reward, but we're just going to take this simple exercise where you have independent rewards for pulling each of the lever. There's an underlying world or truth behind that you don't know. And so your goal as a user is to determine by learning which of the lever gives you the biggest expected reward, right? The reward is a random variable. And then you'll see there are efficient ways to do this. So I would say for next week Friday, so the exercise for Friday is question 1 entirely, and then there's part of question 2. I think there's still some parts of question 2 that needs Markov decision process. I think you'll see them actually as you start working on the coursework, but I think a lot of question 2 can be done. Maybe even question 3. I don't have the coursework with me, but there's some parts that you can start doing now. Right. I think I'm going to stop here. This is a good time. It's been like an hour and a half. Questions before we... Okay, this is about the pace I'm going to follow. So this is kind of going quick, and then it's going to get easier, I think, again, if you do the coursework. For me, I really understood everything when I started coding these things. And coding is really the best way to learn. If you cannot code something that it's on the board, you need to go back to that learning and then trying to understand what it means. As soon as you struggle so much with the coding that as soon as it works and then you've coded it, it's crystal clear. So I really encourage you to go through the coursework. Yeah, so the solutions will be the actual code in Python. Oh, you can do it in whatever language you want. You can even use Fortran if you want, but I wouldn't show it to anybody if you write in Fortran. Yeah, I'll give my own solutions in Python. The code is amazingly simple, right? There's nothing in the solution that actually takes more than half a page of coding. The coding is really easy. Again, once you understand the theory, it's just a bunch of loops put together. There's nothing that goes beyond like 2 nested loops or 3 nested loops at most, but you know. So it's really like making sense of these objects, especially making sense of these concepts in terms of linear algebra. V of S is a function, sure, but it's also a vector. P of S, S prime is a probability transitions, a transition probability, but it's also a matrix, right? So this is where the coursework is useful because it makes you understand these ideas in the way that you can translate all of this into linear algebra and then run this on a computer. But this example, actually, you can play a lot with this. You can imagine, you'll see this in your own simulation, is that you run a simulation that tries to learn the winning lever, but it gets stuck into a suboptimal strategy where it thinks that lever 1 is the winning lever. Just because you had a really rare string of really high rewards from that lever. And then somehow the agent is being fooled to think that lever 1 is the winning lever, right? This can happen. This will be a rare fluke, right? And so you'll see this in simulation, and it's very interesting to see this actually unfolding in time, and then you can just redo the simulations like over and over again. Okay, I'm going to stop here. I'll be here all week, so if you see me, have any questions, don't hesitate to stop me. Umesh, again, is available for question 2 by email. He said he's going to be here next week, so he'll be here in person. His email is on the information sheet that's on the GitHub, so have a look there. My notes, all the scan is actually there too, so you have all the material. Okay, good luck.